So we're going to finish up 3.2 today. And then tomorrow, the plan will be we'll do 3.3 in class because we are not having a in-class test this week. All right, so we're going to keep talking about linear equations. Somebody remind me, what does it mean if you draw something and it's linear? What does it look like? Yeah? A straight line. Now, if it's a linear function, it means it's a straight line, but it can't be what kind of line? It can be any other kind of line except this one. Yep.
I can't go down or up.
And what kind of line is that if it goes up and down?
Parallel?
So parallel is when you talk about two lines next to each other. So we're just talking about a single line. Up and down would be vertical. So for something to be a linear function, it can be any kind of line except vertical. So what we're going to look at now is what is called a solution of a linear equation in two variables. Now, when we write a linear equation in two variables, remember what we're looking for. We don't want to have square roots. We don't want to have multiple x's. We don't want to have exponents on our x's. We don't want to have x's in the bottom of a fraction. We want something that looks like y equals mx plus b. So if I wrote this, if I plugged in 3 for x, what would I get for y? Yep. Not 2. Yeah, I'd get 5. What I just wrote right there is called a solution of a linear equation. Now, are those the only two numbers that you could plug in that work? What do you think, Aiden? You don't have to tell me another one if you think there's another one that works. My question is basically, is this the only pair of numbers you could plug in that would work? No, there are other numbers you could plug in. Basically, you could pick anything you want for x, and then just figure out what y is. So if you plug in 0, you get 2. That is another solution to that linear equation. It's any pair of numbers that you can plug in that make the equation true. If I plug in 0 for x, I get 0 plus 2 is 2, and I get 2 on this side. So if I plug these two numbers in right there, I get a true statement. If you plugged in something like, let's say you tried that. You tried to plug in 1 for x and 4 for y. Well, let's see what happens. Replace the y with 4. Replace the x with 1. Is that a true statement? What do you think, Kate? No. 4 does not equal 1 plus 2. So that is not a solution to this linear equation. Okay. So we have to sometimes figure out, if you're given something, if it is or if it isn't a solution. This one's a little harder up the top of my head, but one solution I could do would be 4, 0. Because if I plug 4 in for x, what's 2 times 4? Well, Abby? What's 2 times 4?
8.
And what are we plugging in for y?
0.
0. What's 3 times 0? Is that true?
Yeah.
Yeah. So this point, if I plug it in, works. All right, so that is a point. That's a solution to that. Now, while we're looking at this, is that a linear equation? 2x plus 3y equals 8. What do you think? Is it the kind of thing we could make it look like y equals mx plus b if we wanted to? Yep.
No.
No? Well, let's try. If you wanted to get y by itself in that equation, what would be your first step?
Divided.
So think of Sam. There's no simplifying because there's no parentheses here. But is there any adding or subtracting you could do before we do multiplication and division to start to get y by itself? Yep. Right, we could subtract the 2x from both sides. That's gone. And now we have 3y equals, you could write 8 minus 2x, but I'm going to write minus 2x plus 8. We want to get in the habit of putting the x1 first and putting the number without the x last. All right, now, how could I finish that up if I wanted to get the y by itself? How about Maya?
Minus 3 from both sides.
So we already did the add subtract, so now we'd be multiplying or dividing.
Divide.
Yeah. We could divide by 3, divide by 3, and divide by 3. And look at what we got. Y equals negative 2/3 x plus 8/3. Natalie, is that y equals mx plus b? Yeah. There's your m. There's your b. So this was an equation that was capable of being rewritten in y equals mx plus b. So this is a line. Okay? Even though it didn't have y by itself to start, we could fix it so it did. So it is considered linear. Now, what if I had this? 2x cubed plus 3y equals 8. Would that be linear? No. When you start putting exponents on the x, no, you can't, that's not linear. You can't do that. Okay? So if we want to graph a linear equation, okay, and this part, I think you guys can just follow along because there's not a spot you have to fill in anything here. But if we want to graph a linear equation, we basically have to find every single point that would make this equation true. Here's 2 of them. Well, we already talked about when you draw a line, how many points are on it? Yep. 2. That's all you could fit on a line? How many points can we fit on a line? Yeah? Yeah, infinitely many. Right? This is a line. This, I mean, there's infinitely many. So basically, to graph a line, we would have to find every single one of them. Well, that's too many to find. So what we usually do is we just find a couple. Right? Maybe we find like 3. And once we find 3, then we can just use, like something that's straight and draw a line right through them. Right? And then we automatically know that it's not only these 3, but it's everything along that line. Okay, so that's how we generally try to draw a line. We find you can do 2, 3 points is a little better, just in case you made a mistake on one of the 2. And then we just connect them. So the graph of a linear equation is a perfectly straight line, and we usually try to find 3 points. So when we've talked about domain, we've done really two kinds of domains. One kind of domain is like we did in the warm-up. You have a set of coordinates, like that. And if I asked you, what is the domain in this problem? What would you tell me? Yeah?
1, 4, and 8.
Yes, the domain is 1, 4, and 8. It is exactly 1, 4, and 8. Nothing else. Not 2, not 6.5, not 3.7. It is 1, 4, and 8. Now, if we take something that looks more like this, and let's draw a picture. Like that. And I asked you, what is the domain of that one? What letter is domain again? Yeah? X. And which way does the x-axis go?
Right.
Right to left. So if I want the domain of that picture, we have to look at how far left and right the picture goes. Well, it goes that far to the left, and it goes that far to the right, and we just have to figure out what those numbers are. How far to the left does it look like it goes? Yeah? 4 would be positive. Negative 4. So it goes as far left as negative 4. And how far right? Yeah? What'd you say? 3. So it goes as far right as 3. And both of the inequality symbols should point at the smaller number. And would they have the equal to under them? Or should I leave the equal to off? Yeah? Yeah, put the equal to. So in the last problem, the domain was exactly 3 values, 1, 4, and 8. In this problem, the domain is everything between negative 4 and positive 3. How many values are there between negative 4 and positive 3? Yep.
7.
More than that. More than 7. Yep. We're counting everything. More than 8. When I say between negative 4 and 3, I mean any possible number you can think of between negative 4 and 3. Anyone have another guess? How many numbers between negative 4 and 3? Yep. Infinite. 1.2, 1.7, 1.9, 1.64213, 2.41519. There's infinitely many numbers between negative 4 and 3. This is a very different kind of domain than this one. This one had exactly 3 values at certain points. This one has every single value between negative 4 and positive 3. When you only have certain values in the domain, you can count them. That is called discrete. When you have an unlimited amount of values in the domain, like between negative 4 and 3, that is called continuous. Right, so on your guided notes, we're going to write that in, and we're going to start with discrete. So discrete is simple. It means that your domain is something you could count. 10 numbers, 3 numbers, 5 numbers, even a million numbers. If you had a million numbers in your domain, that's still discrete. Because you could count a million numbers. It may take a while to count, but you could count it. Counting every number between -4 and +3 is impossible. Because there's an infinite amount of it. You could never count it. So that's not discrete. So on your guided notes where it says, sometimes the domain of a function is discrete, which means it only contains certain numbers, very specific values. So let's graph all the integers from 1 to 5. If I wanted to graph the number 1 on a number line, I would put a dot on the number 1. That's how I represent 1. How would I represent 2? That's the next integer, yeah? Put a dot on 2. Put a dot on 3, 4, and 5. That number line represents the exactly 5 numbers. 1, 2, 3, 4, 5. Does it represent anything between those numbers? What do you think, Emily? Does it represent anything between those numbers? No. If it represented something between them, then I would have shaded between them. But I didn't shade between them. It just represents 1 through 5. So now let's look at what is called continuous. So continuous is when you have so many things you can't even count. It's infinitely many. So a continuous domain includes not just certain numbers, but every number. Fractions, decimals, anything you can think of. So let's graph all the numbers from 1 to 5. Not just the integers. All the numbers. Here's 1. So this is graphing all values from 1 to 5. All right, if I wanted to include 1 as my first one, what symbol would I put on it if I want to include it? An open circle or a closed circle? Closed circle, yep. And I also want to include 5. So would I put an open circle or a closed circle on 5? Open would mean to not include it. Yep, so we want a closed circle. And I want to represent every single number between 1 and 5. So how am I going to do that on my number line? Yeah, I'm going to connect the dots. To represent every number between 1 and 5, essentially what you're doing is this. Put a dot here, a dot here, a dot here. Here, here, here. You're putting infinitely many dots between 1 and 5. So what would that look like? We would just connect it. That's what we call a continuous interval. Another example, like something that might make sense to you of continuous, is your age. Like when you're 14 and you turn 15, you go through every single possible age between 14 and 15. You don't just jump from 14 to 15. At some point, you're 14 and a half. At some time, you're 14 and a quarter. You might be 14.1, 14.2, 14.61. You go through every single age between 14 and 15. Something that's Not continuous would be like if I counted how many people are in this room. 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 20. Well, as I count from 1 to 20, I'm not using every single possible number that exists between 1 and 20. I mean, I didn't go like 1.7, 1.9, 1.926. I skipped all those numbers because when you count, you don't use those numbers. So counting is more discrete. Doesn't use every number. Continuous uses every single number. Okay, so how do we graph a function if we are given certain values in the domain? My hint or my suggestion is going to be to make a table. The table is going to kind of help you organize what you want to do. And the table will have 4 columns. It's actually exactly the 4 columns we did in the warm-up. It's the same idea. Your first column is going to be an x value. Your second column is going to be for a formula. You're going to write a calculation that you need to do. The third column is going to be the answer from that calculation. And the fourth column is going to be the number in the first column, comma, the number in the third column. So the fourth column is the most important one because that's going to give you a coordinate to put on a piece of graph paper. And how many coordinates did I recommend that you find for a line? At least how many? Yeah. You can do 2, but how many did I recommend at a minimum? 3. I would even, if you can do 4 or 5, that's even better. The more points you put, the better you're going to be able to draw your line. But at a minimum, you should always do at least 3. Okay, so first we set up a table. Step 2 is to graph all the points that you just created in the 4th column. Okay, we're going to graph all those points. And the third step is to decide if you have a discrete or a continuous data set. If it's discrete, then you're going to leave your graph just like this. You're going to have dots. You're only going to have a certain amount that you can count. If it's continuous, then you're going to connect the dots. Continuous is like an unlimited amount of dots. There's so many, it looks like a solid line. Whether it's discrete or continuous, we have to read the problem and see what makes sense. If you have a problem about counting the number of people in a room, that's discrete. There's no such thing as 3.4 people. You have 3 or you have 4. There's nothing in between. All right, so we're going to look at example 1. I'm going to change the number a little bit to make this a little easier for us to do on graph paper. When we're graphing things, decimals are kind of hard to do, so I'm gonna fix this one. So let's say we had the function. Again, this isn't as realistic, but it's an easier number to do on paper. Y equals 2x. Y is the cost. X is the number of tickets that you pay for to go into a museum. It says each customer can buy a maximum of 4 tickets. Find the domain. And actually, they don't say to graph it unless that's later on. Yep, it was later on. Okay, so find the domain, and then we'll graph it after that. Okay, so we're going to have X. We're going to have a formula. we're going to have y. And what was the last column? Yeah.
XY.
X, y. Okay. So when we look at this, you're going to have to make your table off to the side of the graph yourself. What's the smallest amount of tickets somebody could choose to buy? Yeah?
None.
They could choose to buy none. Okay, and then we'll figure it out. And what is the most amount of tickets that they can buy? There's a limit on this, yep? They can buy up to 4. Now, if you want, we can look at this part right now. The domain is your x. What does it say x represents in this problem? Yeah?
So the number of tickets you get.
It's the number of tickets. Think about when you go to buy a number of tickets. Can you buy absolutely any single number of tickets? In math, can you buy 3.2, 3.3, 3.7, 4.6 tickets? Or can you only buy certain numbers? Yeah. You can only get whole numbers of tickets. So that tells us right away that this domain is discrete. You can buy 2 tickets, you can buy 3 tickets. You can't buy 2.7 tickets. It doesn't work that way. So now, we're going to fill in our formula. Each one is going to start out y equals, and then fill in the number for x into the formula right next to the 2. 2 times 0, 2 times 1, 2, 3, and 4. The y column is going to be the cost. So now you do the formula out from the second column. What's 2 times 0? 0. What's 2 times 1? 2. 2 times 2? 4. 2 times 3? Yeah. Gives me 6. And 2 times 4 is 8. Now, just to make sure we know what we just did, we found the y's. What do the y's represent in this problem? It's the cost. That's the cost to buy that many tickets. So now, we're going to take each x and y value and turn them into a coordinate. Finnegan, what's my first coordinate going to be?
0, 0.
Perfect. 0, 0. Natalie, what's my next coordinate? 1, 2. Jacinda, what's my third coordinate?
2, 4.
2, 4. Micah, my fourth coordinate? So what's my x value in this row?
30.
And my y value? 6. And Alyssa, how about my last coordinate?
4, 8.
Good, 4, 8. Those are the coordinates. This time we have 5 of them. That's a good amount that we're going to graph. So let's start with 0, 0. That's right at the origin. The next one is 1, 2. How do I graph 1, 2? Yeah? Abby?
Top right column. 1 to the right.
Mm-hmm.
2.
and then up 2. So 1, 2. Then we have 2, 4. So 2, 4, 3, 6, and then 4, 8. So 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. Does it look like those are in a straight line? What do you think? Yep.
Yes.
Yeah. And now, because we said that this is discrete, should I connect the dots or just leave them as dots? What do you think? How about Mia? What do you think? Why? When would we connect them? What would that mean if we connected them? Well, we know it's a function, yes, because we don't have any repeats in the x's, but what's the difference between connecting the dots and not connecting the dots? So, when we talked about that versus that, what's the difference? What does it mean if you connect the dots? Yeah?
Means continuous.
Means it's continuous. In this problem, we said that our domain was discrete. So, should we connect the dots or just leave them as dots? Anna, what do you think? Just leave them as dots. If you connect them, then now you are saying you can buy not only 1 ticket or 2 tickets, but you could buy 1.1 tickets, 1.2 tickets, 1.3 tickets. You can't do that. So since it's discrete, leave them as dots. Think of it that way. Discrete dots. They both begin with D. Discrete dots. Continuous, connect. Right? Think of it that way. CC. Continuous, connect. All right. This one is on the back. It says the linear function m equals 50 minus 9d represents the amount of dollars you have after buying a certain amount of DVDs. So 50, it's kind of like the amount of money you're starting with. And based on that formula, how much is it saying every DVD costs? Like how much are you spending every time you buy another one? Yeah? You're spending basically $9. So we want to figure out if this is discrete or continuous. This time, I'm going to hold off on graphing it. Let's just figure out the domain and if it's discrete or continuous. So we've got the number of DVDs. We've got a formula that we have to figure out. Then we've got M. Now remember, that stands for money. And then I have my coordinate, which is the number of DVDs, comma, money. I know we normally use X and Y, but in this problem, they chose to use D and M for DVDs and money. That makes sense. Okay. What's the smallest amount of DVDs we could buy? Could always choose to buy none. So that means we would have 50 minus 9 times 0. Well, if you don't buy anything, how much money are you left with? Yeah? How much? $50, yeah. And your coordinate is 0, 50. How many you bought, how much money you have left. All right, let's keep going. If we buy 1, we have 50 minus 9 times 1. What's 50 minus 9? Well, Sean, what's 50 minus 9? 41. So if you buy 1, you'll have $41 left. Say we buy 2. 9 times 2 is 18. What's 50 minus 18? Yeah? 32. So if you buy 2, you'll have $32 left. If you buy 3, eventually we're going to run out of money. That's going to be the problem. 9 times 3, you would have spent $27. What's 50 minus 27? Yeah, 23. Very good. So we're getting lower on money. 4. Well, that's 9 times 4 is 36. What's 50 minus 36? Yep.
14.
Let's see. Yeah, 14. Now, I think this is going to be the last one because we only have $14 left. So we can afford one more. 9 times 5 is 45. And what's 50 minus 45? Yep. 5. You don't have enough money left to buy another DVD. Okay, so now, what does it say to do? Find the domain. What's the domain here? Yep.
0, 1, 2, 3, 4, 5.
Anything else? Or is that it?
That's it.
That's it. That's exactly the domain. 0, 1, 2, 3, 4, 5. Since it's only those 6 numbers, does it mean this domain is discrete or continuous? Yeah?
It's discrete.
It's discrete. You can't buy 3.7 DVDs. You can't buy 4.26. This is discrete. I'm just going to hold off on graphing it because I want to take a look at the last example. All right. Any questions on that? Graphing would be a little annoying with the y's because they get kind of big. So we may have to scale our y-axis to go by tens if we were going to graph. Okay. Last one. So it says a cereal bar contains 130 calories. The number of calories consumed is a function of the number of bars you eat. Well, that makes sense. If I eat 1 bar, it's 130. If I eat 2 bars, it's 260. Guys, we still have about 7 minutes. So, just do this last one. Let's think if this represents a linear function. Let's let this be the number of bars, and let's let this side be calories. What if I don't eat any bars? How many calories do I get? Yeah? None. So I'm making a table. I'm just going to do it a little quicker. If I eat 1 bar, how many calories do I get? If I eat the whole bar, yep. 130. What if I eat 2 bars? Yeah? 260. Let's just do 1 more. What if I eat 3 bars? Yep. 390. I could keep going, but if I keep listing these bars out, would I ever get a repeat here with a different amount of calories? Or if I eat 3 bars, it's always 390 calories if it's the same kind of bar. Would I ever get a repeat in the bars? No. You're always going to get different values if you pick a different number of bars. You're never going to get a repeat. Now, So that means it's a linear function. But the next question is the domain discrete or continuous? If I have a bar, do I have to eat the whole bar? Could I eat half the bar? Yeah. Could I eat a quarter of the bar? Yeah. Could I just cut off a little crumb and just eat that? So what do you think the domain is here if I could eat any amount of the bar I wanted? I don't just have to eat the whole bar or eat nothing. I can eat a half of it, a third of it, an eighth of it. I can eat anything. Yeah? This is continuous. So this is a continuous domain because you can eat any amount of the bar you want. And the domain, technically, is anything from 0 as high as you want to go. I mean, if you had 600 bars, I guess you could eat 600 bars. We don't have an upper limit. You could eat as many as you want. So the domain is every number from 0 and up. You could eat 0.4 bars, 0.2 bars, 1.6 bars, 2.4 bars. You could eat any amount you wanted, but it couldn't be negative because you can't eat a negative amount of bars. Okay, so you'll see something like that on the take-home test. So remember, take home. It doesn't cover anything that we did last week. It only covers this week. Okay, when is it due? So tomorrow, which is October 28th at 7:50 a.m. Eastern Time, not California or anywhere else. How long do you have?
2 hours.
Right.
2 hours.
You have 2 total hours to work on it between now and tomorrow. Can you pause it and go back to it?
Yeah.
You can, but what do you want to make sure you do? Close it out. Don't leave the tab open or it's going to keep counting the time. I am after school today if you want to come see me, or if you work on it in your learning support class and you get stuck, you can come see me or ask your learning support teacher during the day. So no homework on Schoology. So no Schoology homework. If you are new, which I think most of you have taken a test before, you're good. If not, I need to get you set up on Schoology.